See, in the dehydration of alcohols, we have seen the use of concentrated sulfuric acid. It is very clear that with concentrated sulfuric acid, we get a ZF product with a rearrangement because carbocation is the intermediate. And now when you go for concentrated H3PO4, I mean phosphoric acid also, it is the same thing. You will get a ZF product along with the rearrangement. Okay. Now let us see the steps involved in this. Now this oxygen in the presence of acid catalyst gets eliminated in the form of water. Let me write that. And finally, we get a positive charge at this point. See, it's a 2-degree carbocation. Yes, of course, there is every possibility of this 2-degree carbocation getting rearranged to a more stable carbocation. So let us take this as a less stable one first. We'll go for the rearrangement later, but for now, what are the possible products from this? Now check out the beta hydrogens. Say this is beta, and even there is another possibility, even this also is a beta carbon, from where we can abstract a hydrogen. Now in this, we get this. Okay, there are two possibilities in this. Let us just give them some number. Let this be possibility A and this beta be the possibility B, right? Now when you go for possibility A, what do you get? Yes, this beta comes into picture and we get a double bond here, right? Now in case of the second possibility, I mean B, hydrogen from this comes into picture. Then of course we get this. Getting some sound. So this is the second possibility. From the 2-degree carbocation, we have these two possibilities. Now let us see whether this can be converted into a more stable one. Okay, 1,2-hydride shift. Let's see. Now this hydrogen goes to the rescue of the positive charge. I mean 1,2-hydride shift, right? Upon which we get a positive charge at this area, at this carbon. Now to this carbon, we have two possibilities. Let me, okay, these two in fact are in the same environment. This beta are in the same environment. There is another beta here. Let me say that this is possibility, okay, let us take C and D. This is in fact possibility C, when this also is possibility C. This is possibility D. Both possibilities C, because both are in the same environment. You can take any of them into consideration, you'll get the same product. I think it is clear. Now let me just go for the product. So it's a 3-degree carbocation. This is of course a more stable one. Now from this more stable one, we get two products. Yes. The product from this C can be given as, of course it will be the same as B, right? It will be the same as B, either this or this, no problem. Both are same. This, okay. Next, we have another possibility D. Now this, all right? So these are the different possibilities that we have. Hope this is clear. This is how you have to analyze a question. So concentrated sulfuric acid, I have given a very interesting discussion. With concentrated phosphoric acid, this is what happens. And we also have some other reagents. Let me give you all those. See, there is a reagent alumina. I told you that in the preparation of ethylene, we go for concentrated sulfuric acid at 170 from ethyl alcohol, or alumina at 350. So with concentrated sulfuric acid, we use a temperature of 170, whereas with alumina, we go for 350. So sulfuric acid is more effective, so is less temperature used. In this case, more temperature. See, even with the alumina also, it's the same formula. ZF with a rearrangement, right? Then I also gave some other, that is aluminium oxide along with pyridine. This. See, alumina along with pyridine, it is little different. Only ZF, but no rearrangement. Very interesting. Getting so many reagents, need to be very cautious. Getting more and more complex. See, with the thorium dioxide. With thorium dioxide, we have another interesting scenario. We have Hoffman product, but no rearrangement. I have so many examples. We'll go for some questions after the preparations and all these. Now there is a thionyl chloride, there is also PCl5. These two, say this is thionyl chloride. SO2Cl2 is sulfuryl chloride, but this is thionyl chloride. Now these two, in fact, are actually meant for converting the OH or the alcohol that is given into halide, which is a very good leaving group. So OH is converted into Cl because of these reagents. So they are just meant for converting alcohols into halides, because halide is a better leaving group. Okay, so with these reagents, these convert OH into Cl, a good leaving group. Okay, so this is about the different types of reagents that we have. Now, let us take some other examples. See, with the thionyl chloride, we can actually take this way. Let me give you an example for the thionyl chloride thing, or PCl5, no problem. So this is isopropyl alcohol. See, when treated with the thionyl chloride, of course, a H plus is lost from here. Then we get CH3, CH, O, S, double bond O, Cl. And then of course the CH. Okay. Now, see, from this, as and when this goes here, Cl minus is lost. As I said, it is a very good leaving group when compared to the regular OH. And we get a carbocation, CH3, CH plus, CH3, right? Along with this, of course, SO2 is what you are eliminating, even the Cl minus. Now this 2-degree carbocation, of course, cannot be rearranged. Simply gives us the alkene. Okay. You can take one of the hydrogens out if you want to show that clearly. Come on, CH2, then take hydrogen. Now this bond comes to the rescue of the positive charge. And of course, a proton is lost. This is how we have to make the mechanism. Okay. Yes. You can just show the elimination of HCl, I mean H plus and Cl minus. Same is the case with PCl5 also. Okay, let me show you. See, with PCl5, okay, remove H plus along with this, and of course you get a bond between these two, CH3, CH, CH3, then this O with phosphorus still having 4 chlorines. Okay, the same way as seen, come on. Okay, so we get CH3, CH plus, then CH3, got a carbocation, then there is a POCl3, P double bond O, okay, Cl, Cl, then Cl, phosphorus oxychloride, and of course Cl minus, right? Now even this also is a carbocation, which of course loses a proton to give the same product. Okay, so that's it. Very simple, very simple. So only thing is the thionyl chloride and PCl5, they are just converting OH into Cl, which is a very good leaving group, which is going off easily, finally giving us the required product. Okay. Yes, these are the dehydrating agents. Next, we'll go for dehalogenation. See, even dehalogenation is of course a kind of elimination only, but let us see. Let us take 1 or 2 examples. We have seen dehydrohalogenation using alcoholic KOH. Now it is dehalogenation. Let me give you 1 or 2 examples on dehalogenation. You know, dehalogenation of vicinal halides. I mean, vicinal, you can also say vicinal dihalides, but vicinal itself refers to the thing that 2 halogen atoms are on adjacent carbon atoms, right? Let me give you. You know, D means removal. Removal of halogen atoms from the adjacent carbon atoms. Let me give you this simple example. Now, in general, the reagent used for dehalogenation is a zinc dust in alcohol. You can also use magnesium, but most frequently we go with the zinc dust in ethanol or an alcohol. See here, the product formed is CH2 double bond CH2. Zn goes along with the 2 chlorines. Let me give you the mechanism that makes it very clear. Now coming to the mechanism, obviously it is E2. Mechanism is E2. We need to be having the thing set anti-periplanar geometry to each other, right? Anti-periplanar. I mean, it is to be noted. Let me give you an example. I mean, give you the mechanism. H, the same thing. It is anti. H, then Cl, then this Cl. Your 1,2-dichloroethane is what is written in this format. So it's very simple. Now let us show the elimination part. As and when this comes here, this goes off, isn't it? Even here also it can be shown this way. So the product formed here is come on. You got HH, you got HH. Of course, one Zn, Zn plus 2 and Cl minus. That will give us ZnCl plus. The other one goes off in the form of Cl minus. To give some clarity, you can take it that way. Let me give you some more examples. Now, if suppose this kind of a thing is taken, okay, CH3, PH, Br, PH, Br, then CH3. Say this, of course, is meso. You can also call it erythroisomer. Erythro when two similar type of atoms are onto the same side. Erythro, of course, meso, because the connectivity is same in case of both the asymmetric carbons. See, in general, try to recall your memory. TAM, trans compound, anti-addition results in a meso compound. It's of course reverse now. You are eliminating, not adding. Come on. In this case, with the zinc dust in alcohol, as I said, it has to be anti-periplanar. You can actually go with the Newman projections, which I've already shown, or else, for now, let me give it this way. CH3, then PH, Br. See, they need to be in anti-periplanar geometry. I think it's better if we go with Newman. Let me give you that only. That can be shown clearly. No problem with this also, it's okay, but that will be little more convenient. Come on. I told you how to convert. CH3, PH, Br, even this CH3, what? Now these two are anyway taken this way. I told you. So take PH here, then Br here. Okay, now it is very cool. So just remove this Br and this one along with the bonded pair. The first one without a bonded pair, I mean in the form of Br plus, the second one with a bonded pair. What do we get? Yes, very simple. First write C double bond C. Come on, CH3. See, this and this are attached to this carbon, right? Let me first write the two things. Now going for the rare carbon, this PH3 and PH and CH3 are connected to the second one, PH, then this CH3. Hope this is clear. Right? And remember, see, CH3 and PH are onto the same side. Yes, of course, they are onto the same side. But the point is, this is your trans compound. I told you that. So a meso one on anti-elimination gives a trans compound. Interesting. Now take trio. Of course, as usual, this is trio. We can just convert CH3, the same compound, PHBr, but this is what we have to change. Yeah, of course, this is trio. Trio is where the similar atoms are onto opposite side. These are from erythros and trios. You can actually see this in the isomerism thing. Now coming to this, let us convert this into, yes, come on, CH3 PHBr from this area as it is, correct? Then see, in this case, take CH3 as it is, but only thing is these two are to be taken this way. Of course, there is one more step in between, but I am skipping that off and writing this straight away by changing their positions like this. Okay. But it has to be taken in an anti-periplanar geometry. So for that sake, I think we need to do this. Come on. Come on. This will go here. One more step. One second. See, that is for getting them onto anti-periplanar geometry, PHBr. Then take this Br here, PH, and what? Yes, CH3 comes here. Yes, 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 it is okay. Now remove this Br in the form of plus with the bonded pair Br minus. I think this is okay. You got two methyl groups onto the same side, two phenyl groups onto the same side. So we'll get a cis isomer. CH3 here, PH here, CH3 here, PH here. It's a cis isomer. So that is dehalogenation using zinc dust in alcohol. Okay. Then one more example. let us consider example with sodium iodide acetone on heating. Take sodium iodide acetone. Told you that acetone is a polar aprotic solvent. Now what do we get? Yes, of course, the product is going to be this. Of course, NABR, then IBR, right? Now let me give you the mechanism. Okay. Yes. Methyl, bromine. Then this. Same is the case. Using I minus, we can take out this bromine without a bonded pair because the bond is going to go this way. And here it is this Br minus. Okay, that's it. We get our product. 2CH3, then this CH3. Plus, of course, I minus, Br plus, and the other Br in the form of Br minus. Okay. This is with sodium iodide acetone. Even the trio and erythro case can be taken here. Okay. Let me just give you the dehydrohalogenation case. Of course, seen in the elimination reactions, but only to just give you some information. Dehydrohalogenation. See, even in this case also, D is removal of hydrogen and halogen atoms from the adjacent carbons. Anyway, this is E2. Okay, so in this case, you know, the reagent used here is alcoholic KOH. We have already used. So dehydrohalogenating reagent is alcoholic KOH, right? Now, even in this case also, the mechanism is anti. E2. They need to be in anti-periplanar geometry. Okay. So let me just give you the same old example with alcoholic KOH. CH3, CH, Br, CH, CH3, then this CH3. See, with alcoholic KOH, which is not a bulky base, so we can just go for sets of product. Let me show you the types of possibilities. Okay, along with this bromine, we can eliminate this hydrogen. There is another possibility. This is say B. Now, the first possibility, getting some noise. Some disturbance. Sahiti, mute. CH2 double bond CH, then CH, CH3, CH3. This is of course Huffman product, as you can see, minor. Then the possibility B, yes, we get major product. A more substituted one, right? Because it is not a bulky base, Huffman product is minor, ZF is major. Okay, so this is dehydrohalogenation. You can use alcoholic KOH. You can also use sodium amide or sodamide. We'll make use of this later. Okay. So this is dehydrohalogenation.